Hello, Stat 200, and welcome to the Lesson 2 overview video. This week, you're going to be learning about turning data into information. These are the key topics that you're going to see this week. First, I recommend that you go back to Lesson 1 and review the types of variables. This week, you're going to be learning about different ways to display data using tables or graphs, and you'll be learning about some of the most common summary statistics. The methods that you use are going to depend on whether you're working with one or two variables and whether those variables are categorical or quantitative. Let's start by reviewing types of variables. Last week, you learned that variables are characteristics that vary. You learned that variables could be categorized as nominal, ordinal, discrete, or continuous. This week, we're just going to be working with the categorical and quantitative categorizations of variables. We'll start with some of the options that you have if you're working with one categorical variable. In terms of graphical displays, you could construct a frequency table. You'll learn how to do this using Minitab Express this week. With one categorical variable, you can also construct a pie chart. Pie charts work best when you have only a few different categories. Another option is a bar chart. Note that in the bar chart, the bars are not touching one another. The gaps between the bars signify that this is a categorical variable. If you're working with two categorical variables, you can construct a two-way contingency table. Here's a contingency table that was constructed using Minitab Express. Note that at the top, the output tells you that rows signify biological sex. So here, the top row is the females, the bottom row is males. The columns refer to the variable of dieting. So this column is all of the individuals who said no, they are not dieting. This column is all of the individuals that said yes, they are dieting. You'll need to pay special attention to the rows and columns, especially when you're working with two variables that might have the same levels. For example, if you're working with two variables that are measured on a yes-no scale, you need to know which one is in the rows and which one is in the columns. Now we'll move on to one quantitative variable. These are three different graphical displays that you can use with one quantitative variable. Minitab Express will construct all of these for you. The first is a dot plot. In this particular dot plot, we can see at the bottom that each symbol represents up to two observations. Depending on your sample size, this footnote could vary. We could also make a histogram. We can see the histogram and the dot plot look very similar. Note that in the histogram, the bars are now touching one another. The third option, which you may or may not have seen before, is a box plot. Let's look at the box plot more closely. So the middle of the box, the line in the middle of the box, is the median. This is the middle value. The bottom of the box is what we call Q1, or the first quartile. This is the 25th percentile. So Q1 separates the bottom 25% from the upper 75%. Q3 is the third quartile. This is the 75th percentile. So it separates the bottom 75% of observations from the top 25% of observations. The distance between Q1 and Q3 is known as the interquartile range, or the IQR for short. This is the middle 50% of observations. Now let's look at the tails, or the whiskers. The bottom whisker is going to extend to the smallest value that is not an outlier. And later in this lesson, you'll learn more about identifying outliers. The top whisker is going to extend to the largest value that is not an outlier. In Minitab Express, the outliers will be symbolized by these stars. We can use a box plot or a histogram or a dot plot to judge the skewness of a distribution. The distribution of a quantitative variable may be described as symmetrical or skewed. So a symmetrical distribution is going to be the same on the left or the right side. The distribution plot that you see here, you'll later learn is known as the normal distribution, which is a special type of symmetrical distribution. Most of the box plots that you'll see in this course will be vertical. So a symmetrical box plot will be one where the top and the bottom are symmetrical. These distributions are skewed to the right. A distribution that is skewed to the right will have more observations on the lower end and a tail that is extending to the upper end. So the direction of the skewness refers to the direction that the tail is pointing. For a histogram, the tail would be pointing to the right. If you're looking at a vertical box plot, such as the one that we have here, the larger whisker will be the one pointing towards the top. A distribution that is skewed to the left will have more observations on the upper end and a tail extending to the lower end. Again, remember that the direction of the skewness is referring to the direction that the tail is extending in. Now, let's move on to measures of central tendency. The measure of central tendency that is appropriate in any given situation depends on whether you're working with quantitative or categorical variables. The mean is also known as the average. This should only be used with quantitative variables. The median, which is the middle value, can be used with quantitative variables. It could also be used with categorical ordinal variables. It cannot be used with nominal level variables because nominal level variables do not have a meaningful order, so it would not be possible to find the middle. The mode, which is the most common value, can be used with any type of variable. It's most commonly used with nominal level variables. In a symmetrical distribution, the mean, the median, and the mode will all be equal. In a skewed distribution, the mean will be pulled in the direction of the tail. So here in our right skewed distribution, the mode is the lowest value, the median is in the middle, and the mean is the highest value. In this distribution that is skewed to the left, the mean is the lowest value, the median is in the middle, and the mode is the highest value. Here we have a distribution plot that I made in Minitab Express. We have two different distributions. We can see that they both have the same mean of 5, but yet they're very different. The difference between these two distributions is in the variability. So the central tendency is the same, but the variability is different. We would say that the variability of the distribution that is the red dashed line is larger than the variability of the distribution that is the solid blue line. Let's look at a few different ways that we can measure variability. The range is the easiest measure of variability to compute. It is the highest observation minus the lowest observation. The interquartile range is the third quartile minus the first quartile. Recall, the first quartile is the 25th percentile, and the third quartile is the 75th percentile. So the interquartile range is essentially the middle 50% of scores. And finally, the variance and standard deviation. These are the formulas that you're going to see in your online notes this week. On your lab assignment, you'll probably need to compute the sample variance and sample standard deviation once, although I will say after this week, you'll always be either given these values or you'll compute them using Minitab Express. The standard deviation is the most commonly used measure of variability for quantitative variables. Recall from earlier that one specific symmetrical distribution is the normal distribution. When we're working with a variable that is normally distributed, we can apply what's known as the empirical rule. According to the empirical rule, 68% of observations will fall within one standard deviation of the mean. 95% of observations will fall within two standard deviations of the mean. And 99.7% of observations will fall within three standard deviations of the mean. We'll be applying the empirical rule for the rest of this semester. This is sometimes known as the 68, 95, 99.7 rule, or some textbooks have narrowed it down to just the 95% rule. You'll see later in the course, 95% is the most commonly used cutoff for confidence intervals or hypothesis tests. So you want to remember for the rest of this course that with a normal distribution, approximately 95% of observations should fall within two standard deviations of the mean. Standard deviation units are sometimes called z-scores. So a z-score is the distance between an observation and the mean in standard deviation units. To compute this, and this formula will be in your online notes this week, you take the observation minus the mean divided by the standard deviation. Let's look at an example. IQ scores have a mean of 100 and a standard deviation of 15. What is the z-score for an individual with an IQ of 120? So the original individual score is 120, the mean is 100, and the standard deviation is 15. Z equals 120 minus 100 divided by 15. This gives us a z-score of 1.333. To interpret this, I would say that this individual has an IQ that is 1.333 standard deviations above the mean. If you're given a z-score, or if you're told where an individual lies in relation to the mean and standard deviation units, you can use that information to find their original score. Again, IQ scores have a mean of 100 and a standard deviation of 15. What is the IQ score that is two standard deviations above the mean? An IQ score that is two standard deviations above the mean will have a z-score of 2. We can plug these values into our formula. 2 times 15 plus 100 equals 130. The IQ score that is two standard deviations above the mean is 130. The last thing that I want to talk about in relation to working with one quantitative variable is outliers. In Minitab Express and many other software packages, outliers will be symbolized by a star. Here on this box plot of height in inches, we can see that the lowest 4 values are outliers. If you're given a histogram or a dot plot, however, Minitab Express and most statistical software packages will not tell you explicitly which values are outliers. This histogram is showing us the same data that the previous box plot did, so we know in this case the bottom 4 values again are outliers. There are different ways to identify outliers. The method that we're going to be using in this class is the same method that Minitab Express uses, and that's known as the IQR method. The online notes will walk you through a few examples of using the IQR method to identify outliers. Let's move on to scenarios involving one quantitative and one categorical variable. In these cases, you can use a side-by-side box plot. Here, I've taken that data set of height in inches, and I've separated it by biological sex. So we have a box plot for females on the left, and a separate box plot for males on the right. We can use these side-by-side box plots to compare central tendency and variability of the two groups. Now we'll look at two quantitative variables. In this lesson, I want you to focus on scatter plots. Your online notes will also talk about correlation and regression, and we'll briefly look at them in this lesson, but lesson 12 at the end of the semester is devoted entirely to correlation and regression. This is a scatter plot. Here we have height on the x or the horizontal axis and weight on the y or the vertical axis. From a scatter plot, we can identify the direction of a relationship. Here we have a positive relationship because as height increases, weight also increases. This is also known as a direct relationship. We can identify the form of a relationship. So in this case, I would say this is a linear relationship. In terms of strength, later we'll learn how to compute the correlation to judge the strength, but just looking at this scatter plot, I would say it's a moderately strong relationship. In terms of outliers, I don't see any clear outliers on this plot. There may be one or two out here that are a little bit beyond the rest, but I don't think they're different enough to be classified as outliers. You'll see the formula for correlation this week. You are not going to be computing correlation by hand in this course. You will be using Minitab Express to compute correlation. This is what you need to know about correlation in this lesson. It must be between -1 and +1. If R, which is the symbol for correlation, is greater than 0, the relationship is positive, in other words, direct. If R is less than 0, the relationship is negative, in other words, indirect. As R approaches 0, the relationship becomes weaker, and as R approaches -1 or +1, the relationship becomes stronger. Correlations are unit-free. So in other words, your x and your y variable do not need to be on the same scale. We can compute the correlation between height in inches and weight in pounds. Even though one is measured in inches and one is measured in pounds, that doesn't matter. X and y are interchangeable. The correlation between height and weight is going to be equal to the correlation between weight and height. Here's a table showing us how to judge the strength of a relationship. Note that in the first column, you're looking at the absolute value of R. In other words, these could be positive or negative correlations. A correlation of R equals 0.46 is a moderate positive correlation. R equals -0.92 is a very strong negative correlation. So the correlation of -0.92 is stronger than the correlation of positive 0.64. R equals 0.02 is a very weak positive correlation. A correlation coefficient gives us information about the direction and the magnitude of a relationship. So the positive or negative will tell you the direction, and then the number itself will give you information about the magnitude or the strength of the relationship. The last topic that you're going to see in this lesson is simple linear regression. Like I said, you're not going to learn how to compute a simple linear regression model until lesson 12, the end of this semester. At this point, I just want to review some high school algebra with you. You might recall the formula y equals mx plus b. This is the formula for a line, where m is the slope, change in y over change in x, and b is the y-intercept. Let's look at an example. Y equals 2x plus 1. So our y-intercept is 1. This tells us where the line is going to cross the y-axis. The slope is 2, so we're going to go up 2 over 1, up 2 over 1, and so on. We'll connect these points, and this is the line of y equals 2x plus 1. When you look at a simple linear regression equation, you should see some similarities. The difference here, though, is primarily in the symbols and in the order that they're traditionally stated. Your simple linear regression line is going to be stated as y hat equals a plus bx. Note that now the x is at the end of the equation. So the y-intercept in this equation is a. The y-intercept is always going to be the value that's standing alone. The slope is b. The slope is always going to be the value that is tied to the x. Again, you'll see much more of this in lesson 12. You won't be computing these regression lines by hand. You will be using Minitab Express. There's a lot of content in Lesson 2. Much of it you may be familiar with. You've probably already seen pie charts and bar charts in your everyday life. What I suggest that you do this week is make yourself a flowchart or some type of other graphical organizer for selecting the correct graph. You'll learn about a lot of different graphs this week. You'll also learn about a few different types of measures of central tendency and variability. None of it is terribly difficult, but there is a lot of it, and students often get mixed up between what graphs are appropriate to use in what situations. So I suggest that you take some time this week to make yourself a graphical organizer. The one that you see here is one that I made in a previous semester for selecting the correct hypothesis test or the correct confidence interval procedure. We're not going to give you the flowchart this week because I think making the flowchart is a really good learning activity. The online notes are already structured so that they are organized based on the type of variable, so you can use that as your starting point. After you make your flowchart, whether it's using technology or by hand, feel free to upload it to the Lesson 2 discussion board this week to share it with your classmates. This is the end of the Lesson 2 overview video. I know it's a lot of content, but being able to make a flowchart or some other sort of outline for this week's content, I think will really help you to stay organized. As always, if you have any questions, please post them to the Lesson 2 discussion board on Canvas.